I just want to do a small section still of the next section. Let's carry on. 6.3 on page 263, the common emitter amplifier. Now this is the amplifier that you're also going to design and build and test and whatever in the lab as well, né? And you're going to be evaluated on that as well. But nothing to fear. If you know the basics, you would know it's nothing to worry about. It's really not difficult. And if you do have questions about the practical work, that's something that you don't understand, you can always ask again in class so that we can talk about it again. Eh? I am not going to build your circuit for you though, but I will explain some of the stuff for you. Nah. Anyway, let's mark the introductory paragraph there again. As you have learned, a BJT can be represented in an AC model circuit. 3 amplifier configurations are the common emitter, the common base, and the common collector. The common emitter configuration has the emitter as the common terminal, which I will show to you just now, or ground to an AC signal. Common emitter amplifiers exhibit high voltage gain and high current gain, some characteristics of a common emitter amplifier. And of course the common collector and common base configurations we will cover in sections still to come. Alright, figure 6.8, common emitter amplifier. We've already established that the type of biasing that's being used here, there's my supply, the 12 volts VCC. I am using a voltage divider R1, R2 to determine my VB, which will also determine then my IBQ. Nah. So if I go and look at the, I'm a bit tangled over here, characteristic curve of a transistor that you've done in chapter 4, né? IC against VCE. Alright, and then you've also learned that basically, or most commonly, transistor is used as a switch or for amplification. Né? Alright, then you establish some parameters. Parameters, transistor being used as a switch in cutoff. I've seen that IC it's going to be equal to 0 because now it is an open switch. Nah. Open switch, then of course there will be no current flowing through there. Nah. So IC is going to be equal to 0, but VCE is going to be equal to what? When the switch is open, measuring the supply. Nah. So I'm tracing back to the supply, so that will be VCC. When I go and close the switch, the parameters will become what? IC will be equal to IC set, the maximum current that can flow through this device in a specific circuit determined by the circuit, and VCE will be equal to what? Should be 0, but because it's not an ideal device, I know this specific book uses approximately 0.2 volts. Unless otherwise specified, we will use 0.2 volts. Alright, then I've seen also if I connect these 2 points, that's called the DC load line. And if I operate between cutoff and saturation, that is where I will do my amplification, linear amplification, which is what I want. If I want to sing over a mic or I want to play a CD player, I want that small signal to be amplified exactly as it was. I don't want distortion on the output. Okay, so because I've seen, if I bias the circuit, in this case I've biased it with a voltage divider bias to get a certain IBQ. It just means it's the base current for Q point, because there's my Q point. So this is what I have here at this stage with no signal still there. I can see that my transistor is already on. Now it's ready to amplify. Then I will add the signal. You can see here's my signal, which will be there, and I have to make sure that my signal is not too large so that it goes into saturation or cutoff. Now then I get distortion again. All right. Okay, there's a few things here extra that that wasn't in the amplifier that you had a look at in chapter 5. I can see there are some capacitors added there. What do you suppose those capacitors are for? What is a capacitor? How does a capacitor react under DC conditions? Remember, I've got a DC voltage here, né? 12 volts DC. Blocks DC, né? Blocks DC. Why do I put a capacitor? This capacitor here and this capacitor here are called coupling capacitors. Couples my amplifier, input signal, output signal. My input signal is not DC, né? In this case, I've got a sinusoidal signal, but even a voice, it's not a DC signal. Changes all the time, né? It's like an AC signal. I don't want my DC to influence my input signal. I block the DC. All right? Coupling capacitor. The same happens on the output. I don't want my DC to interfere with the output. Where in this case, I will connect at RL. It will be a speaker, of course, né? Okay, coupling capacitors. This capacitor, however, is a totally different story. It's called a bypass capacitor, but we will discuss it in a lot of detail in this chapter. Okay, but it's called a bypass capacitor. You can just make a note of that in this stage. All right, now I have biased my circuit. Now I can apply my signal that I want to amplify. All right. So what has happened? Now there was my cue point. Now I apply the signal. Now I can see firstly. What happens? As my sinusoidal signal grows, what is going to happen? That I is going to add to my IBQ. Now, it's riding on the IBQ, so IBQ plus my signal is going to get bigger. You understand what's going to happen? And then I know, I have a formula that says IC is equal to beta DC times IB. Now it's my IBQ plus my signal's IB, so I am increasing IB, né? You agree? As I am increasing IB, what's going to happen to IC? It also has to increase, né? You agree? Now, as IC increases, where's IC on my circuit? It's a collector current, né? There's IC. As IC increases, what is going to happen to the voltage drop over RC? What does Ohm's law state? Voltage drop V is equal to I times R, né? So if IC increases, what's going to happen to VRC? It's Ohm's law, né? Even if we live in South Africa, we don't mess with Ohm's law. I know we mess with a lot of other laws, but we don't mess with Ohm's law. Okay. So if IC increases, VRC increases. Now, and that's what I always tell the students every time I discuss electronics. As long as you know Ohm's laws and Kirchhoff's laws, no problem with electronics. So, what does Kirchhoff's law state? Kirchhoff's voltage law specifically. If I simplify the circuit, let's take that 12 volts and I put the battery here so that it looks more simple. There's my VCC. So I'm basically looking, there's my plus, there's my minus, current flows in that direction. So there's my closed circuit. So what does Kirchhoff's voltage law state? It says if I add all the voltage drops around the circuit, it should be equal to the supply voltage, isn't it? Alright, now let's get back to this. We've seen now that VRC increases as IC increases. Now, if VRC increases, what is going to happen to VC? Remember, what are the volt drops? Volt drops are VRC, VCE, there's a volt drop there as well, and VRE. Those are the 3 volt drops. If I add them together, it should be equal to VCC. That's a C. That's a VCC. Okay, so those are the 3 volt drops. So if to keep this formula still true, if I increase VRC, VRE remains the same. What's got to happen with VC? It's got to go down. Eh? It's got to go down. And I can see it here. Look at this output signal of mine. What's happening? It's moving in the opposite direction. It's amplified, but it's moving in the opposite direction because of Ohm's laws and Kirchhoff's laws. And that is why the input and output signal of a common emitter amplifier is 180 degrees out of phase. It's called phase inversion. All right. Now this phase inversion is also discussed on page 264. Please mark it NB. You have to understand this because this brings together a lot of electronic knowledge, if you can understand this. You actually taught this as well with the common, what was it? What was that feedback circuit? I forgot the name. Can you believe it? Collective feedback biasing. Remember the collective feedback biasing that you've discussed in chapter 5? It works exactly on the same principle. All right, exactly the same principle. But anyway, if I go to page 264, phase inversion, boldly printed in green, explains exactly what I told you now. Let's read it quickly. It says, the output signal is 180 degrees out of phase with the input signal. It starts with that statement. As the input signal voltage changes, as I explained, firstly it increases now. It causes the AC base current to change, resulting in a change in the collector current from its Q point value. If the base current increases, the collector current increases above its Q point value, causing an increase in the volt drop across RC. Exactly what I told you, nah? So I didn't lie. This increase in the voltage across RC means that the voltage at the collector decreases from the Q point. They didn't say why, but I told you it's because of Kirchhoff's voltage laws, nah? So, any change in input signal voltage results in an opposite change in collector signal voltage, which is phase inversion. Okay, make sure that you understand that. Alright, so the next time we will get together, we will discuss, we'll start discussing on page 264 the DC analysis, which you are also familiar with. But let's end this lesson here today. Then we will carry on with 6.3. I just wanted to explain to you at this stage the phase inversion, which is quite an important thing to understand. All right, any questions at this point, ladies and gentlemen?